Welcome back. Here's our last video looking at the sine law. There's one situation we'll encounter with the sine law that's called the ambiguous case. So ambiguous means it's not clear from the information that's given. There's some sort of confusion about the situation. So we already know that if we have all of the sides and angles, that means that we have solved that triangle. Going back to, I think, one of the first videos I showed you that if a question asks you to solve for a triangle, it means get all of the angles and sides figured out. The ambiguous case happens when we have an angle and then the two adjacent sides. And where that comes from is actually when we're doing calculations with sine of an angle. You'll notice if you take out your calculator, let's use the angle of 60, for example. If I take the sine of 60, I get 0.866. If I go ahead and take the sine of 120 degrees, I also get 0.866. Now the problem is if I do my inverse sine function on this number, take a look at what happens. It only gives me 60 degrees. So when we're doing these calculations, our calculators don't spit out the two possible angles that are available to us. So we have to double check and see, well, maybe there's another angle that we missed. Now within the ambiguous case, we actually have a few different scenarios that we can encounter along the way. So remember, we're given an angle and then we're given two side lengths that we know. The problem comes in that I don't know what this angle here is going to be when I spin this piece around. So what I've kind of sketched out here, I've got this angle that I know, and I know that that side is going to continue along this dotted line till we make a triangle. So if we take a look, here's my side A and my side B that are where B is a lot bigger than A. We can see that, well, if I start spinning this around, because I don't know what angle I'm going to have up here, if I start pivoting this line, I can turn it and see, well, if I try to keep it the same length, because that's the whole point, well, I can attach it there. If I kept going, I'm not going to be able to make any other kind of triangle. Okay, so if my second side that's across from the angle that I'm given is longer than the one that I have, I know that I only have one case, or rather that there's only one triangle possible. The ambiguity comes in when we have this side length B being less than side length A. So notice if we look at option A over here, if this side length here is only this long, I can spin it around any way I want. It's never going to reach that dotted line to make a triangle. So in this scenario, I have no triangles possible. For scenario B here, there's one specific length to that line that will make a triangle. So I can spin this around and it will only touch this dotted line in one very specific location. You may have caught on that there's a 90-degree triangle. The final option, that's the most ambiguous of all, is this idea of having two triangles. So you notice if this triangle side length B is that long, without changing how long it is, I can actually spin it around and make a second triangle. Okay, so I notice that I did kind of stretch it a little bit. So what I'm going to do, just to prove a point to you, I'm going to clone this, flip it around, and show you how, even though it's the exact same length, I've got two triangles possible. So we're going to learn how do we deal with all of these options, how does it all fit together, and what's the simplest way to deal with it. Depending which resources you use in Google, they'll tell you things like, okay, well, you have to figure out the height of this triangle, and then from here you can compare this value here to B, and then if it's longer or shorter, and do all of these things. What we're going to do is always assume that two triangles are possible, and there's a really simple set of calculations, literally just adding and subtracting from 180, that'll tell us whether or not that second triangle is possible. Looking at our first example here, I'm going to try to figure out some angles. I have angle A given to me, and I don't know exactly how far this line extends. I'm just going to sketch that I do know that this is 30 degrees, and that 30 degrees is attached to side length B, which is going to be 6. And then I've got side length A over here that's going to be 2. Okay, I know that this is A and this is B. because this is angle A, and angle A and side A have to be across from each other. Okay, trying to draw a good diagram for ourselves, you can see 2 is really, really short, and no matter how I spin that line around, it's not going to reach this dotted line to give me a triangle. We can use the sine law and actually show how that works. Angle B is what we're looking for, and that would be if this triangle continued, that'd be out over here. So let's do sine B over B. It's going to give us sine A over A. I have all of my angles inside A and B there, so I can plug in those values and start the equation. We've set up our values. We'll do a little bit of algebra to get sine B by itself. And that's 6 over 2. That's going to give me 3 times sine 30. Throw that into a calculator. So I'll do 3 times 30 sine, because that's the order I need to do things in on this calculator. And I'm going to get that sine B equals 1.5. Now I want to get the angle for B by itself, which means I have to do the inverse function of sine. So I'm going to take that 1.5, second function, sine, and lo and behold, something didn't work. And that's actually what it's supposed to do. If you stop and think about SOHCAHTOA old-fashioned trig with right angle triangles, sine is always my opposite over hypotenuse. Well, if the hypotenuse is always supposed to be my longest side, this means this fraction should always be less than 1. So here I am trying to find an angle for which I'm going to get a sine value bigger than 1, and that's physically impossible. Just like this triangle here would be physically impossible to make. So we got this error, and we can interpret that. That tells us some information. We didn't do anything wrong. We just learned from this that we have to take a look at the values, analyze them, and now we can come to the conclusion that there's no triangles possible. And obviously, if there's no triangles possible, then we don't have to bother to check if a second triangle is possible. Here's another example with the same scenario. Go ahead and pause the video, do the work, and I'm going to do one of those quick step-throughs to finish this example off. So we should end up with no triangle possible. You could have stopped at this point here and just made a statement, sine theta, or B, I guess, bigger than 1, and then made the same conclusion that no triangles were possible. Let's try another example here. The punchline's given away that there's going to be one solution, but go ahead and pause the video and try this setup. No matter what, the setup is always the same for any sine law question. So let's take a minute, write it out for yourself, and see how it compares. Let's see how you set up the equations. I'll still step through everything so that you can see the process and how these values came to be. All the same steps as before, nothing new. Now we have that our angle B is equal to 90 degrees. And when we're dealing with ambiguous case triangles, so the side-side angle, the only time we're going to get, sorry, not the only time, but one of the times where you'll know there's only one solution is if there's 90 degrees involved in one of your corners. So B equals 90 degrees, I know that I have one solution. That's because this line here, if I were to spin it around and tilt it, pivot it from this corner to see when it reached this dotted line, there's only going to be one specific location where that happens, where they meet, and it'll be a 90-degree angle. Now to deal with the two solution options. This all comes from, like I said before, the fact that your calculator can't tell the difference when you're dealing with obtuse angles, so angles that are bigger than 90 degrees but less than 180. I use the example of 60 degrees and 120 degrees, and you'll notice that those two values are off by 180 degrees. I'm sorry, I should clarify that. If I did 180 minus 60 degrees, I'm going to get 120 degrees. So that's the relationship between them. So if I get sine of an angle, and that angle is A, Well, sine of a or 180 minus a is going to be the same. That's where that challenge comes in for us. Looking at the example, I'm going to start with the same setup where I know one angle, I know one side that's attached to it, and then the side that's across from it. I'm going to go ahead and label those values. That part's easy. We're going to work through this the same way we have before. Let's solve for angle B. Treat this as another chance for some practice. Pause the video, do the work, and then see the step-by-steps to compare how yours worked out. Now we've done all the calculations, and our calculator told us that when I took the inverse sine of that number, I'm going to get 42 degrees. Here we have to stop and ask ourselves, well, what if our calculator did actually give us two values? What would that second value be? Well, we know that it's going to be 180 minus the value that we just figured out. So 180 minus that 42 degrees gives us 138 degrees. And what we can do is then check, well, what if I take the inverse sine, or sorry, the sine of 138? What does that end up giving me? That gives us 0.667, and that's the same if we had done the sine of 42 degrees. So we have to check and say, well, what if this angle B, we see that it's going to be 42 degrees and make this obtuse triangle here where I've got this big angle here, if this one here was 42. But then what if I actually was able to swing it around and make a triangle like this? And so that this angle B in there would be 138 degrees. Is that actually a possibility? The way I like to check here is to say, well, if a second B value is possible, let's call it B2, it's 138 degrees, I still have to make a triangle, and all of the angles inside of my triangle have to add up to 180 degrees. So do I have enough degrees left over from my 180 if I've used up 138 for B2, plus I still have my 30 from A? So I need to do 180 minus 138 minus my A value, which was 30, because then this will give me, well, what's that second option? If I have two triangles, what would my C corner be? Over here, I can see that I'm going to have C some sort of obtuse value. I would do 180 minus 42 minus 30. That's easy enough to do. But here I got to double check, well, do I have enough left over? And I do, because if I could make this second triangle, that angle C would be 12 degrees. So that means I have two options for triangles here. So I can go ahead and say, yep, I do actually have that second triangle. And then I report two values for B, and I can label them 1 and 2 if I want. I've got 42 degrees, and I've also got 138 degrees as a possibility. Let's take a look at this next example and talk about the process that we need to follow in order to solve it. First thing we need to do is sine law the way we usually do, and we're going to solve for the angle in question. If we're dealing with an ambiguous case, so for instance, I've got two sides and the angle that's attached to one end of them, then I have to figure out, well, what if a second triangle was possible? We know that that second triangle, that angle that we just solved for, well, it has a second option. It would be 180 minus what we just calculated. What we need to do is figure out what's the third angle in the triangle. Remember, when we have a triangle, if I know two angles, I can always get the third by doing 180 minus those other two. So in this first step, the bit of work that we would have done, we would have solved for what I'm calling D1, right? Our first D value, possibly the only one. If I had a second one, I know what it would be, and then I got to look at the third angle in the triangle. So if I knew what, if I was just looking at that first triangle, obviously that F value would just be 180 minus E minus whatever I calculated for my first version of the D angle. Now I want to see, well, what would it be if I did have a second triangle possible? We're going to look at this answer. Obviously, if you get a real number here, then that will be the angle of F in your second triangle. If I ended up getting a negative number here, well, that means I've run out of angles within my triangle. I don't have enough degrees for there to be a second option for the third angle. Okay, so if there's a second triangle, there's also a second value for that F angle. Pause the video and give this a try for yourself. Remember, the first part is the same as what we've been doing. The second part is really, really simple arithmetic. All you're doing is subtracting numbers from 180. You just got to know what those numbers mean when you see them. A lot of people will set up their triangles just like this, so I'm going to do this example this way as well. Now we're checking and seeing what's going to happen with this second possible triangle. In order to see if the second triangle with the D angle of 132 degrees is possible, I need to figure out, well, what would angle F be if the second triangle existed? In order to do that, I'm going to do 180 minus the other two angles in the triangle. There's enough angles or enough degrees out of 180 left over for F to be 14 degrees, so that tells me that I do in fact have two possible values for D. So I could say D equals 48 degrees, and it also equals 132 degrees. I want to go back just for a minute to the example on page 9. It was one of our first examples of a side-side angle triangle, and I wanted to show you how this check that I've been talking about, this second triangle, how to check if it's possible using this example as well. So we're going to set it up just like we did from before. In fact, I'm probably just going to copy and paste a lot of that. So like I said, copy and pasting, here's that work that we did before. I can take a look at this and look and figure out if I wanted to that, well, this C would be 180 minus 16 minus 125, and I could calculate this C value in this triangle. Now what I want to do is say, well, is there a second triangle possible? If there was a second possible triangle, well, that B value would be 180 minus 16, which gives us 164 degrees. Okay, so then I say, well, if this second triangle is possible, that means a second value for angle C would have to exist, in which case I'm going to have to do 180 minus the other two angles. So minus A minus that second B. Well, I'm going to do 180 minus 125 minus 164, and this is way, way, way more than 180 degrees if I combine those. In fact, I'm left with that if this second triangle was possible, C would have a measure of negative 109 degrees. And we know that's impossible. So by doing this check, I can see that there's no second triangle possible. I've got one example left for us to work on. I'm going to step through it. I'm going to go ahead, have you guys pause the video, and then that'll be it. Now, after all that, we see that a second triangle would be possible because there's a second option available for C if we use this second B value. And so that means I can finally give my final answer that B equals 65 degrees, and it also equals 115 degrees. Thanks for going through all this, you guys. We'll see you in the next class.